According to whom? हाँ,
Good evening, everyone. Thank you for attending this presentation. Today, me and my group will share our research on the comparative analysis of two arithmetic logic units architecture, one built using conventional methods and other using Vedical mathematical principles. The working explores how ancient, fast algorithms from Vedic mathematics, when embedded directly in hardware, might solve modern digital design challenges and study investigates execution times, propagation delay, and hardware efficiency, all critical for fast, scalable, and digital systems. The abstract is the goal of this research was to directly compare a standard 8-bit ALU using binary arithmetic for operations like addition, subtraction, multiplication, and division with Vedic mathematic based ALU that employs sutras such as Urdhva Digyabham for multiplication and Nikhilam for subtraction. Both designs were created, simulated, and synthesized in Verilog HDL using the same test conditions. Our main finding is that the Vedic ALU demonstrates lower delay and better parallelism with the most pronounced improvements in multiplication and in design requiring greater stability. Next slide, please. Introduction. Arithmetical, arithmetic logic units or ALUs are the core computational units in every processor. They execute all basic arithmetic and logic instructions. Modern constraints means ALUs must not only be accurate and reliable, but also fast and efficient in terms of area and traditional ALUs, despite extensive optimization, are limited by sequential logic and carry propagation bottlenecks, particularly as operand size grow. Vedic mathematics, a system developed in ancient India, introduced algorithm shortcuts that are highly parallelizable and designed using Verilog. So we were motivated to see whether bringing other ancient wisdom and modern hardware could unlock new benefits in speed and hardware economy. Now over to Manas.
to Shraddha. Problem. Yeah, so the central challenge motivating this study is the increasing demand for high-speed, low-latency computation in embedded and digital systems. Conventional ALUs, while robust, struggle with cumulative delays, especially in multiplication, resulting in efficiency losses that scale as bit width increases. With the technology moving rapidly towards compact devices and high throughput processors, the question arises, can Vedic algorithms, when implemented at the hardware level, provide measurable improvements over standard designs in terms of speed, area, and scalability? Next slide, please. This brings us to our objectives. First, to design, implement, and test two 8-bit ALU architectures, one based on conventional binary logic and the other on Vedic mathematics. Both ALUs needed to support addition, subtraction, multiplication, and division. Second, to compare the performance side by side, measuring not just execution time and propagation delay, but also hardware resource use, scalability, and error handling. Next slide, please. Our methodology followed standard design and evaluation practice with an emphasis on fairness and transparency. We designed both ALUs in Verilog HDL coding for the exact same operations, input sizes, and output format. Both conventional and Vedic ALUs supported full binary addition, subtraction, multiplication, division, and logical operations. The conventional ALU uses the ripple carry adder, standard shift and add multiplication, and restoring division. For the Vedic ALU, multiplication leverages the Urdhva Tiryakbhyam Sutra, which calculates products using parallel, vertical, and crosswise steps. For subtraction, the Nikilam approach is optionally used. We use the same synthesized tools and test benches for both, ensuring identical input operand sets and evaluation environments. Finally, we analyzed execution delay in nanoseconds, hardware area by gate count or resource utilization, and functional robustness, including error handling. Now, over.
Now, results. On the result, both ALUs exhibited the same memory footprint, 28 bits, including operation code, two operands, and the result. Simulation revealed that all operations, addition, subtraction, multiplication, and division, complete in 10 nanoseconds at the 8-bit scale for both architectures. Schematic diagram shows that while the traditional ALU is more linear in logic flow, the Vedic version has higher internal parallelism. Edge cases were considered for the example in division by zero, and both ALUs handled such cases robustly. Perhaps most important, though, speed parity was observed 8-bit simulations. The Vedic architecture's modular and parallel designs is expected to offer greater savings in delay and resource consumption as the operand size increases. Synthesized module and the comparison table support these trends. Conclusion. To conclude, this comparative study shows that both designs are equally capable at small bits in terms of speed and memory use, largely because modern synthesize tools optimize standard logic aggressively. However, the Vedic approach provides a distinct architectural advantage for scaling to a wider operands due to its inherent parallelism and favor sequential dependencies. As digital systems demand ever more performance per watt and per square millimeter, Vedic ALUs offer a promising foundation for the next generation of lower power high throughput and scalable hardware solution, blending ancient mathematical algorithm with modern technology. References. These are some of the reference research paper we have referred to. Thank you.